Welcome to the last session, everyone. With Mark, we talked about building blocks, but here we are again building blocks, but now we're making houses.
I'm a test consultant. I work in Endava. And today we have a little bit catchy and descriptive title. We build a house. Now let's make sure the neighbors don't walk straight into the kitchen. You may ask, how is that related to technical stuff? And I may tell you there is a strong analogy there, because the house in our speech today will be our application. Our client is basically the user. Neighbors represents our clients, our users. Everything in between will be something that we will discuss. So there won't be discussed around the kitchen, the dining room, the balcony. Those are the features that our application offers. We will speak about the backyard, the front yard, the fence, the front door, the back door, the sidewalks around our house, the roads that are leading us to our house. So, why those things are important? Because if we implement those properly, our application will tend to be bulletproof, let's say like that. By having all those implemented properly, we will increase the performance, the reliability, the usability, the scalability of our application. I'll move now to next slide, as basically that will give you the proper representation on what will we talk now. First thing is that is only one example. There are many implementations on many different platforms. We will cover many of them today, but additional point that I want to tell you, I'm not a complete subject expert in all of them. Yeah, I use them, but I'm not a subject expert. The point to our session today will be to extend the wider image and to raise awareness on how that is implemented and what might be the issues if we implement all those things wrong. So we are here. We'll represent sort of a GKE or Kubernetes environment where we have 3 pods where application is running. So application is on 3 places, and we have 3 pods on 1 node. And that is great. And we may have multiple requests. There should be something that should delegate all those requests to our pods, to instances of our app. Something like that is load balancer. There are also a few things in between load balancer and our pods. You will see on the later slides. And that is still in-house. We are responsible for that. Then we have end users, and we have downstreams of our app. Let's discuss first of the downstreams, right? We need to ping downstreams. If our downstreams are in the house, that is easier. Why? Because it is in the house. We control all of that. But if we need to ping external third-party dependency, a situation becomes a little bit complicated. Why? Because it is not allowed for us to directly ping the third party. That's not a good practice. So we will have a proxy server in between that will handle that communication and will be responsible for outbound traffic. Also, on the other side, when the requests are coming to us, external requests, we need to have some front door in order to receive that request and then forward it in the house, in our environment, so that it consequentially finishes on a meme of Mr. Bean. So timeouts and retries. We usually define the timeouts on application level, right? And we may put 5 seconds there. But if all the layers above our app have timeouts, and they will have it for sure, if that timeout is not meeting the one on application level, so if it is less than one we have on application level, we will have issue. In ideal case scenario, everything will work as expected. We will meet the standards, 200 milliseconds, perfect. But in case of delays, there will be an issue. Our client will see an error. But that error won't be thrown by application. It will be thrown by upper layers. Because 4 seconds passed, application is still running. Maybe application would get the response, but basically we missed the timeout on upper layers. And that is an issue. Also, in terms of retries, that may affect the performance and too many retries. Now, the issue that may happen with headers, bodies, and protocols. All of those have some security mechanisms, some checks that they are doing. They may be aware of some headers, and they may ignore some. But also they may remove some headers or normalize them or remove special characters when they're proxying it to the later layers. And you're asking me, okay, how that may be an issue. And I'm going to tell you, okay, if we have Nginx on the front, which trim the headers, and our application depends on those headers, we won't see those headers on application level. And our application will throw an error. Again, our client will see that error. It will report an incident, and then we need to analyze what had happened. By knowing all these things, that is something that I should tell at the beginning. If we know all that, it would be, let's say, easier for us as developers to take decisions on application and testers to take decision on application level, and it would be easier for them as well to implement the things. So for the headers, we covered that part, and this pretty dog tells us about the security and identity. Usually, when we have incoming requests, and that stands also for outgoing ones as well, we will perform some authentication that will be covered by certificates, by MTLS, the traffic will be encrypted, everything will be secured. Even if we miss the version of the TLS they are using and the one we have on our service, that may cause issues. And the request won't pass through our door in that case. And now, in terms of connectivity, that rabbit represents the performance. So we may implement our app to process 1,000 requests per second. But in case we didn't define our front door, our front yard, the street that comes to our house properly, we won't be able to receive 1,000 requests. We will be able to receive 100, 250, based on what have we configured there. So that means, yeah, our application works and may handle that, but we will never have that traffic. As we disable, it needs to ensure the performant workaround, the stable workaround, and it needs to ensure the scalability, let's say so. And how it does that? It will distribute the traffic across all available instances. How it operates, on which level it operates. It may operate on the L4 or L7 level, depending on how we are doing that balancing. And it works based on some well-known algorithms. You have an option. You may inherit the load balancer from the environment on which your application lives, or you may implement your own. You may use one of the well-known algorithms, and that is the common case, or you may implement your own. So I added here a few of them, like round robin, that will send a request to each instance in sequence, so first, second, third, and that is how it works. Then it may work based on least connections per pod, so the request will go to instance that has the least open connections. Then it may be aware of the resources that our pods are consuming, so the request will be sent to the pod with the least consumed resources. Basically, there are many of them, like I told you. There are geographic algorithms that distribute the traffic based on location. But now, what are the main purposes? Why should we implement load balancer at all? Why should we have 3 pods and not only one? Logic answer is absolutely the performance, but basically it will distribute the traffic. It will ensure that not a single instance will become overwhelmed. It will also ensure the scalability. So during the deploys, we will deploy the new code. So in terms of Kubernetes, new pods will be created, right? But the old ones will be deleted. And we need to ensure that even though that release may last for 1 minute or 1 hour, it's 1 minute usually, but I'm giving you some examples, we need to ensure that we don't have any traffic loss. And that is responsibility of load balancer. So it will be aware of the health of all the pods that it points to that are available, and it will know where to send all those requests. So that's how we won't have any traffic lost. Whenever the new pod becomes available, perfect, it will have many more pods or instances to send requests to. Again, performance, zero downtime deployments, we covered all that with this pitch, and also the security. Like I mentioned, security may be implemented on all those layers, depending on what you want to achieve and what is the agreement on your end. Now, we are again coming to a part, how can knowing all that help me? This is something that we want to escape with the proper implementation of load balancing and with the proper implementation and choice of the load balancing algorithm. In this case, we had 3 pods. Our application processed huge files, so that was not transactional service. It processed few files over a day. The files were coming externally. And there are 2 types of operation. One is, okay, I identify the file, I will store it at my system. And another one, I will load the files in my memory, I'll process that and update something. We received 6 files, or 7, or 8, no matter what. But I know that at that case, as this is real life example, all the huge requests, so the files that consumed most of the memory when they were loaded in the application's memory, were processed by one single node. Round robin was used there as an algorithm, and you see that we indeed had 2 pods that were relaxing there. And they were like, I don't care. But that guy over there processed close to the limits. We reached out the memory limits, and you may tell me, yeah, but we didn't reach the limit. And I may tell you, yeah, but we didn't know that that day we won't have 2 more files. And in case those finished on that application, even the garbage collector won't help us, as basically the memory will be consumed for some period of time. And all of those will finish on that instance at that time. We may discuss about optimization on application level, but in that case, changing the load balancing algorithm was the choice. And basically, here is what we want to avoid. We want to achieve that all those available pods use the equal amount of resources, process the same amount of requests, so that our environment is not stressed no matter of traffic. Okay. Now, let me drink a little bit of water. Not because I forgot what to tell, I'm thirsty. So, incoming and outgoing traffic. When something comes to us from externally, yeah, that is external traffic from the eyes of our environment and application. When we want to ping the third party downstream, that is external traffic. In that way, we have the traffic direction. Client sends a request to our application sends the traffic to the external dependencies. In terms of incoming traffic, that is a so-called reverse proxy. In terms of external traffic, that is called so-called proxy server or forward proxy. And in terms of are they exposed or not, external one, so reverse proxy is exposed, and forward proxy is not exposed. Their responsibilities is basically to control the incoming traffic and to control the outgoing traffic, front door and back door. So in our house, where are we at the moment? Front door should be our gate, fence and the gate, so all our neighbors should come through the front door. And in terms of the back door, yeah, that's pretty much clear what's the back door on our house. In terms of what you may use for one thing or another, I provided a few examples there. So for the reverse proxy, you may use Nginx Plus, Nginx, APG, and many different services. In terms of forward proxy, like I said, Squid, S-Tunnel, again, Nginx, the most common word used today. By me, at least by me. And now we can make some differences. There are many similar things between those two. But in terms of the incoming traffic, just to repeat, the goal is to accept the traffic and to route it to proper services in our house. And basically, the goal is to provide security and don't pass something that should not should to our system. So in that regard, some TLS checks may be done there. We may check the headers. We may do some authentication there. And we will route our requests to below levels in our flow. And in terms of the common issues that may appear there, like I said, timeouts, mismatched headers, if they are sending the requests, even though we intended to expose some of our features, some of our endpoints, and we did not configure that properly there, and our client is sending us requests, that request will be rejected. If they miss some authorization details, the request will be declined. Similar thing stands on the other end of the outgoing traffic, but in this case, we are representing ourselves to the third party. They will have the same talk that we did so far on their end, but from our perspective, we will have egress that will handle our requests and send them to the third-party dependency. So how it works, like I told you, it manages the connections that our application intends to make to a third-party dependency, and it is particularly responsible for the security, as usually that traffic is encrypted, is protected by some certificates, it's protected with MTLS. So all those checks are done there. And if your application needs that, logically that should be maintained and provided and implemented at that level. So if we need to provide some specific host header, it would be good, it's possible to handle it on the application level, but it would be good to implement it there. Also, where we point, also the certificates, all those things should be secured, let's say so, and should be on that level. Now, about the common features, I covered that part with this speech now, so I won't repeat it. But in terms of the common issues, that is basically the DNS resolution, misconfiguration there, misconfiguration in certificates, misconfiguration in the timeouts, in the headers, in what are we supposed to send to that third party in order that third party to allow us to use their features. Now, some examples that I found interesting. Those are only few of them. Like I said at the beginning, there might be several implementations. I'll move on that side, and as I don't have a pointer. So the first thing above is the incoming traffic. So we have two endpoints on our application, and those are exposed by using two different services, two Nginxes in this case. For the first endpoint, when the request comes, we will validate the certificate. There is MTLS and there is IP whitelisting. The second one has only the IP whitelisting, but that implementation is quite expensive. Why? Because there is a way to have only one service that will handle all that incoming traffic. So to have one Nginx in my example, that will have configuration per endpoint, and you will save the money, as one more pod, one more Nginx means more money. You may have many different front doors. Yeah, I mentioned Nginx, you may have APG. That's also something I mentioned. On the other side, the example here represents the outgoing traffic. So that is something that I mentioned before. Headers should be, in this example, headers, certificates, that is how we represent there, and MTLS is enabled. So all that should be handled on that way. If there is some mandatory header, our application may send that header and Nginx may inherit it, or it may be configured on that level. Now, two things at the end, two examples at the end. This one represents the many users, as basically our application may be used by some other service, but our application may be exposed to the real users. So we will have many requests. We need to ensure performance. And in that case, we will again open the reverse proxy and connectivity to our application. And depending on the service we choose, we may have many different validations, like I told you. So it is possible to validate the body, to validate the headers, from where that request is coming. It is possible to have dual authorization. So we will give some keys to our clients or to third upstreams to use some key when they ping our front door. Then our front door will recognize that. It may do validation over IPs or many more things. And it will say, OK, that traffic comes from Mike. Mike has reserved place on our application with some different key set or different authorization mechanisms. And it will change that request a little bit, optimize it, and that request will be sent to our application. Again, that is also potential potential place of misconfiguration, but it also increases security. And this guy here, with that guy, I wanted to tell you that situation may become even more complex if you have multiple layers of load balancing. So if you use APG, that's really cool service. It has its own UI, and you are implementing policies on your own. And that guy has its own load balancer. So you have load balancer on that end. That will distribute the traffic. Then the traffic comes to your app, but I provided here only the app, and you remember the initial graph. So if we have 3 instances of our application, there will be a load balancer in front of it. So we will have multiple layers of the load balancing. And in case we mismatch some things, misconfigure some things there, again, we may have multiple issues. Now, security, the most important part. That is a bulldog in front of our gate that is protecting us from intruders. What is WAF? Web Application Firewall. It will go through each request that comes to our application, and it will analyze that. In case that request is invalid, it will be rejected. Basically, it won't be rejected if we don't turn on that feature, as basically WAF works in 3 different ways. First one is monitoring, where it will indeed report the issue with your request. It may work in blocking mode, where basically the invalid request will be blocked, and that's it. There won't be a pass for them. And in the era of AI, the learning mode, when it will monitor for some time, create the perfect policy for your environment so that you can use it later. And basically, that is how it works. And it protects our application logic. So it works on application layer. We may implement WAF on many places in the flow. On my graph, I put it at my front door. But like I told you, it may be implemented on many different places. And here, you will find the real-life example. So those 2 requests were completely legit, and they passed the WAF, and they finished on the origin server, where our application lives. But that guy, that one is blocked. So there won't be there will be response for that guy, but that one won't reach the origin server. And that is how WAF is protecting us. So about the main purposes, we explained how it works. But about main purposes, it is protecting us, he is aware of, and it's protecting us from the top 10 OWASP threats, like SQL injections, XSSs, and all those things that the malicious users uses to attack our system. It will validate both input and output. So even though if our request body contains some malicious things, that request will be rejected. That is something that is indeed required if we worked with sensitive details. So in order to get the PCI DSS compliance ladder, we will need to implement that guy. That is important for the GDPR, and if we indeed want to protect our system. It may also reveal some vulnerabilities that our system has and that we are not aware of. And that is how WAF is working. It may also detect some attacks if they will try to use the brute force to get into our system. And at the end, this is the takeout. I'll come to that part. but at the end, most common issues and what may happen if you misconfigure the WAF. So false positives at the first place, as basically there might be some requests that should pass the WAF. As WAF in some occasions may not be aware of how that request should look like. Maybe there should be some special character that our application expects to be at that place. That is something that we need to implement within our policy in order to work. Again, on the other side, there might be some things like with encrypted traffic that WAF is not aware of as well. But the biggest issue there is that in order to perform that analysis, as I said to you, WAF is intercepting each request. And in order to analyze it, it will spend some resources, memory and CPU. It may go as deep as you want, but that will spend a lot of memory and resources. And performance overhead is the one issue that appears here. Why? Because usually WAF has the limit, default one is 8 kilobytes, which means even though your request is bigger than 8 kilobytes, WAF will analyze only the 8 kilobytes. That parameter is configurable, just to be clear. You may put 1 kilobyte there, 10 kilobytes, whatever you want. But increasing that number will increase the resources and will increase the time that is needed to process your request. And we need to meet standards. So the default, like I told you, is 8 kilobytes, which means what? There might be an issue. Which issue? This guy here. That request should pass the WAF, and that is perfect. But that request contained the malicious things in it after that limit. WAF was not aware of that, and he just passed that request, even though it should fail. And that is something that is known, and that is something that malicious users are using commonly in order to break into our system. And why is that important for us? And you can ask me why we are implementing WAF when it has the thing like that, vulnerability. Because indeed, it will increase the security and the bulletproofness of our application. But we also need to be aware of the following thing. Even though we implemented security on multiple levels there, we cannot guarantee and we cannot rely on that. We need to implement protection and protecting mechanisms in our application as well. As to overcome that issue, we may implement some protection mechanisms on our application. Performance will be still met, and basically, even though the request will be passed to our system will reject it. And you may ask me, okay, may that be over-engineering? And I'll tell you, yeah, but in really, really, really small amount of cases. In most of the times, it will enhance the security and how our application indeed works. And basically, that was all that I wanted to tell you today. And yeah, we have some time for questions.
So thank you for this amazing session. We might have time for a question or two. So if anyone has a question in public, raise your hand. If not, you can just write down.
Will we give him a microphone? In any case, you can find me tomorrow at the Endava corner, so we can hang out and discuss.
So about load balancers, you mentioned that it's possible to stack layers, like to have multiple layers of load balancers, right? So is it always only one of them that is exposed and responsible for receiving connections from application, or we need to secure all of them and to take care about security for all layers?
That is a question for a long discussion. A long story short answer would be yes, depending on what you want to achieve. So if you have application that is completely in-house, that is called by your environment and other, if you are in the microservice architecture, right? You have 50 microservices. One may be completely in-house that is used by all others. And that guy may have 5 instances. Surely it will have load balancer in front of it. And that one won't be exposed. Usually load balancers are not exposed. You have a front door that will ping that load balancer. But yeah, we may discuss. I would like to involve some DevOps if they are present here, just to give their opinion on that. I hope I answered your question. Yeah?
Thank you. That will be it for this session and this day. If you have any other questions, you can ask them later. So see you tomorrow.